The law of conservation of matter or mass is the next thing we're going to look at right here. We're going to talk about an example where we use some stoichiometry, which is a relationship quantitatively between the particular species in a chemical reaction. And we're going to discuss how you can evaluate a chemical reaction equation. So in this chemical reaction that we have here, we're going to discuss the law of conservation of mass, or the sum of the masses of the reactants, which are on the left of the arrow in this equation here. Reactants on the left, products on the right. We're going to talk about how if you add up the masses of reactants, that you're going to get an equal mass of product. So for example, we're going to show how if you react 75 grams of propane, C3H8, with say about 272 grams of oxygen gas, that you're going to produce about 225 grams of carbon dioxide and about 122 grams of H2O. I don't remember the exact numbers, but we're going to kind of show that process. If you add these up on this side and you add these up on this side, you get the same number, the same quantity of mass. So in a chemical reaction, the sum of the masses and the sum of the products are equal. And again, remember, reactants are on the left, products on the right. So that's kind of like a basic chemical reaction format. So we're going to start out with these components here. Anytime you combust a hydrocarbon in the presence of oxygen to completion, you get carbon dioxide and water. So those are your products of burning this propane. So we're going to start out, when we look at this kind of problem, first of all, we make sure it's balanced. This one's already balanced for you. You'll also have to balance equations before you do this, but right now we're going to start with one that's already balanced. Balanced means that there's the same number of each type of atom on both sides, reactant and product. So you're not destroying any elements, any matter, and you're not putting new elements in and products that weren't in the reactants. So the first thing that we should do is probably just start out and calculate the molar mass of each individual species. And that just goes by the formula. So whereas we did before, if you have 3 carbons and 8 hydrogens, your molar mass, each carbon is 12.01 and each hydrogen is 1.008. And if you're going to multiply that out, you got 3 times 12.01 plus 8 multiplied by 1.008, and you get your 44.094, but you're only going to be allowed 2 decimal places, so you would report that as 44.09, and that unit is grams per mole. Now your oxygen, there's just 2 oxygens there. Your oxygens are 16.00 each, so that's 32.00 grams per mole. And then on the product side, you have carbon dioxide, so 1 C and 2 O's, and you do the same procedure on that, and you get 44.01 grams per mole. And then here You do your water, H2O, so there's 2 hydrogens, 1 oxygen. It comes out to 18.016, but we only get 2 decimal places, so we would call it 18.02 grams per mole. So this is your, one of your first steps. First you balance it, or you can calculate your molar masses for each species, and that's a very important thing to do. Now, when you're just calculating molar mass, you do not multiply by the coefficient that's in front of the balancing part of, that makes the equation balanced. That's for something else later. That's to establish what we call mole ratios, which we'll use in our proof as we try to summarize this kind of thing right here, and show mathematically how it's correct. But first step, calculate your molar masses, and that way you have that to work with. It's important to have those. You know that molar mass can be used as a conversion factor to convert grams to moles, which is an important step of what we're going to do when we start doing this stoichiometry part of it. The other thing is your balanced equation does provide coefficients that tell you how many moles of something goes with how many moles of your other things. So basically you can create these mole ratios. Mole ratios are a very important part of stoichiometry, what we're going to be doing throughout the whole part of the course actually. But it is important to establish mole ratios. But you can only do that once you've balanced the equation with the proper coefficients, which we'll do a lot of that in practice. But since this one's already balanced for you, we can look at what the mole ratios are. So I can look at that equation and I can say, 1 mole of C3H8 will require 5 moles of oxygen to completely react it. So that's a mole ratio we can use. And you can flip that around like you could write it the other way. 5 moles of oxygen for 1 mole of propane. So you can flip it whichever way you need to do the math. So you can also looking at this, your propane, compare it to how much carbon dioxide you're going to produce. So 1 mole of C3H8, if it's completely combusted, will produce 3 moles of carbon dioxide. You could also make that relationship between propane and water. So every 1 mole of propane completely combusted will produce 4 moles of water. You could also do relationships between oxygen and carbon dioxide and oxygen and water, or mole ratio for carbon dioxide to water. So if you look at that equation, you can get an actual total of 6 mole ratios, and then if you write them the other direction, flip them around, reciprocal, you actually would have 12. So if you count them like that, but you can have 6 mole ratios that then can be reciprocal to give you 12 mole ratios. So we're going to look at a particular type of problem that I just sketched out real quick up here, and I'm going to see if the numbers come out to be that. So over here, if you added this to that, on that side, you get 347 grams of reactants, and over here, if you add that together, you also get 347 grams of products. So we're going to just see if that comes out to be about right when we do this problem, when we're actually going to say we have a given mass of propane that we're starting out with. So you start out with your 75.00 grams of C3H8. This just starts out just the same way we've been doing a lot of the other dimensional analysis. And the first thing that you need to do is convert these grams to moles. And I want to see, if I can get to how many grams of oxygen. So you start out with this. You want to convert to moles of this. So you go up here to use your molar mass. You're like, okay, 44.09 grams of C3H8 is 1 mole of C3H8. And that lets you get to moles. You have to get to moles of this stuff, of this one reactant, before you can start talking about this other reactant. But once you get to moles, and we have, this mole ratio that relates propane to oxygen in terms of moles, then I can use that conversion factor, and I'm going to put the C3H8 part in the bottom. So 1 mole of C3H8 requires 5 moles of O2. And then I can start talking about my oxygen now. So that's where that little mole ratio came in. That's why that stoichiometry part is so important. If I'm going to really burn that much propane, if I have to know how much oxygen I need, you don't want to have too little oxygen, because then you end up making, well, carbon monoxide could be a possible product of that. And carbon monoxide, you probably heard, is not good for you. So it's could kill you. It will kill you. So this is what we're talking about, completely combusting. So now we're in moles of oxygen, and the problem says how many grams of oxygen are required. So now, since we've got moles, we can use molar mass to go from moles back to grams. So 1 mole of oxygen is 32.00 grams of oxygen. And now we're in grams, and we can approximate our answer to 4 significant figures. And then if you want to calculate that on your calculator, that's just fine. You have your 75.00 grams. As you're working your way across there, the next thing is I would go across the top, and I say, oh, I got to multiply that by 5, because the 5's on the top with it. And I've also got to multiply that by 32. And then I have to divide that by what's on the bottom, which is your 44.09. That's your molar mass of your propane. And you get 272.2. So to 4 sig figs. So approximate that as 272.2 grams of O2. Which, if you look up here, that's about what that was. So very good. So there's one part of it. So that's how you would get to that part. Now I just carry this over because you could also determine how, based on that 75 grams of propane that you had, how much carbon dioxide would theoretically be produced and how much water would theoretically be produced. So I just brought my molar masses over from the previous calculations, and I'm going to use those along with the mole ratios to finish out this kind of problem, just to talk about, these are what we're going to talk about. This is a yield, right? This arrow means yield, so you could say that 1 mole of propane reacts with 5 moles of oxygen to yield 3 moles of CO2 and 4 moles of water. So we're going to talk about our yields now, our product, how much product could theoretically be made of each one of these. And we're basing that off of completely combusting 75.00 grams of C3H8. Okay, so this part doesn't change. We still have to convert this to moles. So your first step is just like in the previous part where you convert it to moles. So we're using our molar mass as a conversion factor to get to moles, which goes with your little chart that I showed you in an earlier video, which would be a good thing to have in your notes, some kind of little chart like that, just to remind you of how to get from one place to another. Okay, so here we're in moles of propane. But now I said I wanted you to start talking about how that relates to products. So I want to use mole ratios between propane and, say, carbon dioxide. So I want to stop talking about propane and see how much CO2 I'm going to make. So here I'm going to say 1 mole of propane, because that's from my balanced equation, will produce 3 moles of CO2. Now I'm predicting my yields for carbon dioxide from completely burning that. So I'm in moles, and if I want grams, I just use this molar mass as a conversion. So 1 mole of CO2 is 44.01 grams of CO2. And your moles cancel out, and you're in grams. So now we can approximate that. And again, you have to multiply the things on the top and then divide it by what's on the bottom. So, but you don't have to multiply by 1 or divide by 1. So it's going to be 75 times 3 times that, and then divide it by this. So pull up my calculator. 75. I'm not going to put 0.00, so it's not going to change my answer. And then I'm going to multiply that by 3, and then by your 44.01. And then I'm going to divide by the molar mass of propane, because that's on the bottom. And I get 224.6. Because I get 4 sig figs. And that's grams of CO2. And if you remember, go back to my previous slide there, I said about 225, so that's close. Alright. And then here, we're going to do this one more time to talk about water. How much water are we going to produce? Now I could predict this since I have all the other 3 numbers without doing this step, but just to show that it works. So we're going to start out the same exact way. And we're going to convert that to moles using our molar mass. Grams cancel. Then I'm going to use my mole ratio between water and propane. So 1 mole from my balanced equation for that, and 4 moles of water. And now I'm talking about water. So molar mass of water is 18.02 grams of water. And I'm going to do the exact same thing in my calculator. Multiply this times 4 times 18.02, and I'm going to divide by your 44.09. Oops. $122.6. That 1 won't make that 6 round up, so I'm going to just round it to right there. 122, so I'm going to say approximately 122.6 grams of water. So if you go to check your law of conservation of mass, you have 75 grams. Well, like it's 75.00, so I guess I will do that right here, of propane. And then we calculated our oxygen in the previous part was 272.2. And then our 224.6 grams of CO2 and 122.6 grams of water. So if you add this up on this side, you get 75 plus 272.2, that's 347.2. You only get one decimal place because when you're adding or subtracting, but that's your grams of your reactants total. Remember, law of conservation of mass, the sum of, that's why you add them. So now let's see if that equals this. So I add this up here, I get the exact same thing. Now that's grams of product. So my product's mass over here is the same as my reactant's mass over here. So that's why having a balanced chemical reaction is going to be very important. But also it starts out by just being able to calculate a molar mass. And then we'll throw in some mole ratios, and we'll do that throughout the semester as well. But this procedure is exactly what chemistry talks about. So practice this until you're comfortable, and you can do, if you're given this, at least this much information, that you can derive the law of conservation of matter and law of conservation of mass, and be accurate when you're done.